person can easily identify which animal is in this image. As for a computer, until recently, this was not an easy task. However, with the advent of the neural networks, the solution to this problem has been simplified and significantly advanced. Let's consider a simple case of classifying this photo. Since this is a raster image, it can be represented as a matrix, where each value is a pixel brightness. We will fit this matrix into a neural network. Depending on the pixel value, nodes of the neural network are activated, which in turn are connected to the next layer of the network, the hidden layer. In a sequential or feed-forward network, each layer serves as an input for the next layer. The number of nodes in the last layer corresponds to the number of the classes that the entire network can recognize. In our case, it's a binary classification, cat or dog. In the end, the node with the highest value is chosen. This node corresponds to the label dog. Let's consider the properties of a simple network using a linear model, in which there are only two layers, input and output, and correlate the formula with the graphical representation. X denotes the input of the node and takes values 0 or 1, which corresponds to the on and off position. The weights are shown on the edges of the graph and indicate the significance of the nodes. The bias is displayed within the node. The output shows the state of the node, just as for input node. Using a neural network, you can simulate other functions. For instance, a function that takes an animal image as an input, and then you get the name of the animal as output. Consider the XOR function. All possible input and output values for this function are shown in the table. We can represent the same values on the plane, where the axes represent the input values of the function and the color of the point corresponds to the output of the function. Let's try to simulate the function with our linear neural network by drawing a line that will divide all the points into two classes, red and green. It seems like it didn't work out this time. On both sides there are points with the different colors. Maybe the function values were not chosen correctly. Let's try the others. It doesn't work again. The thing is that our XOR function is nonlinear, and we can't simulate a nonlinear function with a linear one. Moreover, in 1989, George Sebenko proved that no matter how complex is our linear neural network, it still could be approximated with a single linear function. The activation function can rectify the situation. The neural network with the nonlinear activation function and a single hidden layer could approximate any continuous function. Of course, if there are enough hidden units in the layer and weight and bias is selected correctly. Let's dive a bit deeper into activation functions. We can highlight the following types of activation functions: step function or heaviside function. That's the simplest activation function. It has only two values, 1 if the argument is greater than 0 and 0 in all other cases. Sigmoid function. Previously, it was one of the most popular activation functions. The range of the output values is from 0 to 1. ReLU function. This is currently the most popular activation function. It has gained the widespread use due to its simplicity and efficiency in the calculations. GLU function. In its form, it resembles ReLU function. However, the transition from negative values is smoothed out. Experimental results showed that the convergence and the performance of the neural networks improved compared to ReLU. But let's return to the step function that we will use in our neural network. Consider an example of the neural network performing the XOR function. The network will consist of 3 layers: input, hidden, and output. Worth to mention that all weights and biases are not random, but selected during the model training using the gradient descent algorithm. The training process will be explained in the next lectures. In the first iteration, 2 positive signals are passed to the input, which are then transmitted to the hidden layer. We will be conducting calculations of the neural network node values on the right-hand side. The values of the nodes in the hidden layer are positive, therefore both nodes are activated. The node of the last layer of the network takes a negative value, so we get the value of 0 at the output, which corresponds to the XOR function. In the second and the third iteration, one of the nodes is active. As a result, we get a value of 1 at the output. In the last iteration, both nodes are inactive, and the output value is 0. Thus, our neural network model fully simulates the XOR function. The calculation shown is quite tedious, and their number is large even for such a simple network. In reality, neural networks are calculated through the matrix equations, which are particularly effective on the graphic cards. To understand the difference in efficiency, let's perform the same calculations but in vector form. For this, we will convert the weights and biases of the neural network into matrices. We could perform calculations for every input argument individually, but it is more effective to combine them in a single batch and calculate all possible output at once. The third step is to determine the values of the hidden layer. Then we repeat the calculations for the last layer of the neural network and get all the possible values for the XOR function immediately. Let's see what has changed in our task when we used a linear function and then added an activation function and another hidden layer. This is how the linear neural network originally looked like. As we confirmed earlier, it isn't possible to solve such a task using a linear function. Let's add an activation function and a hidden layer. After the changes, the axes no longer represent the original inputs, x1 and x2, but the neurons of the hidden layer, h1 and h2. Now the output value of the network depends on them. For a such task, it's easy to find a solution and draw a line separating the points by color. Thank you for your attention.